of definitions, and the properties of colloids are based on they are having a different shapes. Because of that, they are having a different properties also. And we have seen the differences, and we have seen the preparation method of lyophilic. It is as good as simple solution. Lyophobic, we have got a dispersion method, that is size reduction method, that is top a bigger particle to smaller particle. Condensation is bottom to top approach, that is solution to dispersion form, sol to dispersion form. First we will take a solution converting into a dispersion by precipitating it. Precipitation method. Now the precipitation method can be attained by the two types. One is change in the solvent, another one is a chemical reaction. Change in the solvent, which is the anti-solvent, which will precipitate the solute, make the precipitate in the colloidal region. Because of that reason, we are going to get this lyophobic colloid. Another one is a chemical reaction. In the chemical reaction, both the reagents are soluble. They are present in a solution form. When they are mixed, they react with each other, form a molecule. That molecule is in the range of colloidal region. That is the reason we are going to get a chemical reaction as a preparation method to prepare a lyophobic colloid. And we have already learnt the purification of colloid because when you are taking individual electrolytes, they are present in the soluble form. But when you are taking the same thing in precipitated, some of the electrolytes they will be getting precipitated, some may be present as such as a electrolytes. These electrolytes will act as a impurities, and we need to remove them, because we have already told we are going to use this concept for the anti-cancer drugs and specific one which is having a particularly targeting to a particular tumor. So we are selecting some colloidal region as a size range. In those cases, if you are having a drug which is not present in the colloidal form and present in the simple solution form, it will produce the toxicity. In those cases, we will purify it, remove the free soluble form of such things, so that we will be having a 100% targeting to tumor. This is actually required whenever we are preparing specific purposes. For that purpose, we are using three approaches. One is dialysis. This is the diagram we are seeing, and it is having some four sides, and the electrolytes are passing towards the free solvent, that is the pure solvent you are distributing. Because of the change in the concentration differences, it will be moving. And ultrafiltration, it is same as that of your filter, but the filter paper is having very smaller opening, that is aperture size. This is made by the collodion impregnation. This like trinitrate is a collodion. It is made from the cotton fibers. When you are having impregnation with that, you are going to have very small particle size. Because of that reason, you can retain colloids and you can pass your electrolytes and other soluble components to purify it. The third approach is very faster method, in that we are applying the electricity to attract charged species of our ions. So we are using electrodialysis. This is actually what we have discussed in the previous class. Very important for the exam, because sometimes they will be asking in a 5 marks question either purification or preparation separately. In 10 marks question, both preparation and purification of your colloids. Now, you may get the question, sir, if it is asked only preparation, do I need to write purification also? Preparation method means you have got this preparation method for the lyophilic cask or association, what it is a lyophobic, that you need to see. If it is not specifically asked, you need to write all the three. So you need to mention little bit about these mentions about these methods are available for the purification, not to be elaborated if it is not asked separately. Depending upon how many marks which you have got a weightage, you are going to attempt that particular question. Because a purification is also a part of a preparation method. They will be asking preparation and purification of your colloids. It will be present particularly pertaining to lyophobic only. We are not going to deal the same thing lyophobic only, because it is having a particle size of a definite region and it is present in the particulate matter. The third one is association or amphiphilic colloid. It is a very different approach when compared to above two. It is appearing as a globule, that is not a particle, it is a globule size, and it is actually nothing but a micelle. It is not a particle, it is not a molecular dispersion, it is a micelle. It is a different approach. In this, the micelles are formed by having a lyophobic component present as a core, and around the core you have got a lyophilic component, that is having, it has got a dual role. It is containing dual, both lyophilic and lyophobic components in that particular molecule. Sometimes it is having a both the ion characteristics. In amino acids, proteins, we have got a both anion and cationic functional groups. Because of that reason, we are going to have the surfactant, surface active agents, to form a particular micelle. So in the micelle, we have got a definite size. That size is in the range, in the order of 50 angstroms. 50 angstroms are equivalent to 5 nanometers. So 5 nanometer is in the range of 1 nanometer to 500 nanometers. So we are calling it as a colloidal dispersion only. And each one which has got some aggregation number. What is the aggregation number? When you are adding any surface active agent, after getting some molecules, they will be having solubility, they will be dissolved. You are adding some more excess, then they will start merging into some number of molecules formed as a micelle. That number is called as the aggregation number of a micelle. So this aggregation number is depending upon the type of conditions what we are going to use, and the concentration of the monomer, and the critical micellar concentration where it is attaining. Most of the times we will be having impact of your pH and electrolytes. That is the reason we need to keep them controlled. And important point in this particular case is a craft point. Why this is very important to us is, craft point, we need to pick up a particular temperature. At that particular temperature, your critical micellar concentration and your solubility is same. Because of that reason, you are going to have very excess of formation of your micelles at the craft point, and your solubility of your surfactant will rise manifold. Generally, when you are adding a solute to a solution, it will be forming and it will take some time to get dissolved, but at the craft point, it will take too much of solute to get converted into a solution very fast. So this craft point will help us like enhancement of the solubility of poorly water soluble drugs by inserting them in the core of your lyophobic in nature. That in the lyophobic nature core, it will be taking your lyophobic drugs, that is water insoluble drugs, make them bioavailable. This craft point is very important. So you do remember this craft point pertaining to the colloidal dispersion in the GPAT. In the GPAT, what is the craft point, or what is the temperature at which the solubility of surfactant is equal to CMC, and sometimes what is the application of craft point. So this concept is used to solubilize the poorly water soluble drugs to enhance the bioavailability. Now we are coming to our actual topic. Why I have gone back is, you need to know the properties of colloids which you are not able to get reply. So we are taking it back. We have got 3 types of properties which are existing. One is optical property, and the second one is electrical property. The third one is kinetic property. So optical, kinetic, electrical properties are peculiarly which is present in the colloids and not in the solution and not in the dispersion. So that is the reason we have got this specific question in the exam, and you are going to be asked. So one such thing is the Tyndall effect. In the Tyndall effect, you are going to form a beam or a cone of that particular beam is appearing in the dark background. You can see only in the colloidal dispersion with the visible eye by viewing against a dark background. This one is observed only in colloidal dispersions, not in your solutions and in your macro, that is Poisson dispersions, that you don't have this effect will be there, will not be there. And this is actually what a depiction of a picture, and it is also having turbidity. This turbidity will be appearing in force dispersion also, and the light scattering, but the light scattering will be present in all the cases, but the concentration is there more, and you don't find that in the remaining two types, like a solution and your coarse dispersion. In the solution it will be appearing as a transparent, and in the coarse dispersion it is completely hazy and opaque, it will absorb. But the scattering effect will be more prominent phenomena in the colloidal dispersion, where you can detect the light in the 90-degree angle to the source of light that is present in the dark field microscope and ultra microscope. Generally, if you are seeing your pharmacognosy lab or in your biology lab, you might have seen you are exposing your light through the mirror, and directly you are viewing in the eyepiece. All are in one direction, that is vertical 180 angle. But you can't see the light in 90 angle, because when you are focusing a light, the beam of light will be going towards the eye in the vertical angle. But in the dark field microscope, what you see, you will view the light 90-degree angle to your source of light, what you are exposing. This is actually what the peculiarity of this particular microscope, that is ultra microscope, where you can observe the light scattering. You can find the light waves which are appearing, and you can see the movement of your colloidal dispersions. They are having a Brownian motion. You can see them. This is actually what the dark field microscopy. In the dark field, your field will not appear as a light. In your regular one, you will be having entire field is a light, and in the wherever the particle is present, it will dark. In the dark field microscopy, entire field is dark. Wherever the particles are present, moving, they will be appearing as a lightening, because they will be scattering it. They are reflecting and scattering it in all the directions. The light is viewed there against the dark background of that microscope. This is actually reverse of what you are seeing in the biology lab and in your regular laboratory. This is a peculiar effect which is observed only in the colloidal dispersions, light scattering. Kinetic properties we have seen. The kinetic properties peculiar to this one is Brownian motion. In the Brownian motion, we have got the molecules and the particles are moving as they like in all the directions and hitting to each other and taking their diversion of their paths. They will be hitting and taking a zigzag path. This zigzag path, it will be seen easily in the ultra microscope, in the dark field microscope. So they will be moving as they like and keep on moving. The second phenomena is the diffusion. A diffusion phenomena is very much important for our drug delivery system functioning, because it is taking a drug and diffusing through the biological membrane and reaching the target. Because of that reason, we are applying a different laws. The Fick's first law is applicable here, and there are different parameters we have seen. And why this is very important to us in this particular case is a Stokes-Einstein equation. This Stokes-Einstein equation, it is giving a diffusion coefficient. The diffusion coefficient is containing some more parameters like your temperature and viscosity and the particle diameter. It is linked, and Avogadro number and 6 pi are the constants. So these are all the things which will be resulting into some questions we are going to have. The velocity of the molecule increases with the direction. This is actually what the equation says. The three main rules are going to come, and the velocity of the molecule is more, that is increases with the reduction in the particles is obvious, because the R is in the denominator, inversely proportional relationship. Velocity of the molecule increase with the increasing the temperature. In the diffusion coefficient, you have got a T in the numerator, that is directly proportional relationship. The velocity of the molecule decreases with the increasing the viscosity, because in your diffusion coefficient, viscosity is having in the denominator, it is having an inversely proportional relationship. Another one is the osmotic pressure. This osmotic pressure we are applying to not to allow your liquid to pass through the semi-permeable membrane when the semi-permeable membrane is separating your pure solvent with the solution. In the case of this is a colloidal solution or a colloidal dispersion. This osmotic pressure is also present here. Osmotic pressure is applicable to solutions also. In the regular solutions also it is applicable, but provided if the molecular weight of that particular solute is more than the pore size of your semi-permeable membrane. If it is less than the semi-permeable membrane, it won't have any osmotic pressure. It will just cross. It will just cross through the membrane. But in the colloidal dispersion, as the size is bigger, so you are going to have obviously osmotic pressure. In the regular solution, in all the solution, you don't observe this. When very smaller particles are present, they will be having. But when the semi-permeable membrane is having a pore size very lesser in nature, then solvent will diffuse and osmotic pressure will also be present there also. So it is not unique to this. This parameter is not unique, like a Tyndall effect. Tyndall effect is unique to colloidal dispersion. Here you need to understand Van 't Hoff equation. I have already told you, you are having a condensed form of your textbook and your chapter is a PPT slides. The condensed form of a PPT slides is writing down all your general concepts, like your critical micellar concentration, Kraft point, aggregation number, and Stokes equation, Stokes-Einstein equation, Van 't Hoff equation. These are all the one which you need to write it separately. This entire around 100 slides or it may be 60 slides converted into one paper. That one will be very useful for your GPAT. It means whenever you are completing it, seeing your PowerPoint presentation or a textbook, you convert that entire chapter into one page of your own handwritten notes. This is actually what the preparation for GPAT. So this preparation in the GPAT, when you are having it, then you will be having a less problem at the end of your reading before going to your GPAT exam. So you are going to read only your papers what you have written, not the textbook before going to the GPAT exam. So in the Van 't Hoff equation, we have got the C R into T. R is a constant, T is the temperature which you can know, and osmotic pressure is directly proportional there to the C. Why it is important to us is because the C is present, we can replace the C with Cg by M. Because of the Cg by M, that is the concentration of the grams of the per solute per liter of solution. M is the molecular weight. We can determine the M, unknown M. When you know the Cg, when you know the R, when you know the T temperature, R is the constant, so T is the temperature, you know it, and pi you know it, then you can determine the just simple M. So you will be having osmotic pressure determination by equipment, you determine it, you calculate the molecular weight. This is actually what the importance of Van 't Hoff equation to find the molecular weight of your colloids when you prepared them. Another one is the sedimentation. In this we have got a Stokes equation, and the Stokes equation is the one which is applicable to the sedimentation of the particle and rate of falling. It is against the Brownian motion, because Brownian motion is against your gravity, that is acceleration due to gravity. This one which will be present, a peculiarity to the colloidal is you don't find a sediment easily. That is the reason you are applying ultracentrifuge, which is having 10 to the power of 6 times more force than the gravitational force. So if the centrifugal force is dominating, you are going to have a sedimentation formed. So this is the same as that of your upper equation Stokes law, when the G is replaced with W square into X. X is your diameter of your centrifuge and W square is your angular acceleration. So how many times, that is depending upon your RPM and how much is the time of your rotation in the centrifuge. Another one is the viscosity. This one you have got in the previous week. I hope you are getting this one. I wanted to come back to the slide back. You have done this one in the Monday's practical. What you have done, you have taken eta of a unknown solution, that is a glycerin solution. Eta naught is a water. you are taking it, and which is having a replace, that is the Einstein equation of the flow, which is giving a relationship between these two is eta, that is any viscosity of any solution, which we are giving is equivalent to viscosity of its solvent multiplied with 1 plus 2.55. The 5 is the fraction of colloidal particles. How much is the fraction of the colloidal particles are presented? The fraction of colloidal particle is linked to your C, that is concentration of the particles, that is your molecules. This volume fraction is defined as the volume of the particle divided by the total volume of the dispersion. That is the reason you have got relative viscosity. This relative viscosity also you have calculated on that day. So that value is equivalent to 1 plus 2.55. So that phi, it will be giving you the concentration term to you. If you are replacing that equation, what you have got there, you can calculate the phi there. I did not ask you to do it, but I left you there in the eta divided by eta naught. So by applying this relative viscosity 1 plus, then you are taking this relative viscosity 1 to that side, then you are having a 2.55 and you are dividing the 2.55, then you will get a phi. That is volume fraction of your particles. But we are not tried that, but we have calculated and reported the relative viscosity. We have also calculated specific viscosity, that is n specific. What you have done? N by eta naught minus 1. This is one formula you can do it, or eta minus eta naught divided by eta naught. This is actually what you have done, the expanded portion. So you have taken eta naught in the denominator, in the numerator you have got eta minus eta naught, because eta naught relative viscosity minus 1 is equivalent to your specific viscosity. This specific viscosity is having relationship with 2.55. So you divide the specific viscosity by 2.55, you will get again phi. This is actually what the beauty in the viscosity of your colloidal dispersion contributed by the your solute fraction. So another concept what we have seen, because the solute fraction is proportional to the C, n specific divided by the C is equal to 2.5. Why we are converting it to a C? Because it is depending upon the concentration. This part we are going to do in the next practical. Up to this part you have done already, up to specific viscosity you have already reported. What you have done? Absolute viscosity, relative viscosity, specific viscosity you have done, and we are going to do the remaining portion like intrinsic viscosity and the reduced viscosity, intrinsic viscosity for all solution in the next practical. So this n specific divided by C is equal to 2.5. This part we are going to do, and this one is very useful because we are going to use in the case of C. We are converting into a molecular weight also. We can convert and we can get the molecular weight, or we can put this and calculate the unknown viscosity by simple equation. This is one thing which we are going to have by determining the intrinsic viscosity. So what is this intrinsic viscosity? You need to plot n, that is specific viscosity, by the C on the y-axis and C in the x-axis. You will get a straight line that is extrapolated to the y-axis. Then you, whatever the intercept is called as the intrinsic viscosity. So this intrinsic viscosity is going to help you where to determine your molecular weight. How? It is having a linkage with intrinsic viscosity is equal to K into Ma to the power of A. So molecular weight, this is given as an equation, log intrinsic viscosity is equal to log K plus A into log of M. A into logarithm of M. So if you know the intrinsic viscosity from the plot, if you know A and K, you can determine the molecular weight. Unknown molecular weight also you can determine. Even anything which has been given to you, the solution, you will calculate intrinsic viscosity. I will give you the value of K and K. I will ask you to determine the molecular weight of solute, what I have given as a sample to you. You can calculate. You see how beauty it is without doing elemental analysis, without finding what elements are present, and without touching any equipment, just by doing this practical by your hand, by simple your Ostwald viscometer, by using the phenomena, by knowing K and A, you can determine the molecular weight of any unknown compound. This is what the concept of science, which will make the life very easy. So if we plot reduced viscosity, that is intrinsic viscosity versus log of m, then the slope is A and intercept is K. If both are known, you can determine the unknown m. If you A and K are not known, you take m from the osmotic pressure or sedimentation method, or it is the diffusion method. You calculate the m and plot against squared eta, that is the intrinsic viscosity. Then you will get A and K. If you know them already, then you can determine the m. If you don't know A and K, you determine the m and you put the value, find the value of A and K. So these are all the things which will make determination of one parameter, which is possible if you are having remaining parameters are known. This is in the equation of what you have already seen here. This theta is equal to K into m in m to the power of A. Now we are having electrical properties. We have seen your optical property. We have seen kinetic properties. There are 5 properties in the kinetics. You have already seen the 5 properties. So these 5 properties are given one by one. One is Brownian motion, another one is diffusion, another one is osmotic pressure, and sedimentation and viscosity. They are all applicable to the flow. That is the reason we are calling it the kinetic properties of colloid. Why I am telling this is a 10 marks question you are going to get in the bigger mark, so the bigger one. And in the GPAT you are going to ask some problems like this. They will be giving A and K. They will ask you to determine the molecular weight. So they will give the intrinsic viscosity. They will give the slope and intercept. They will find out, ask you to find out some more equations or that values. You need to fill there. There is small problems only. It will be asked in the GPAT like that. You will be having a question in the sessional, and this you are going to have a bigger question explaining all. And the third property is very much important, is electrical property, which is deciding our formation of colloids and your properties of your colloids and purification of colloids, which will be made easy. I hope now you have got something till now what you have understood, and you are going to read your PowerPoint, which I have shared as a link, and we are entering into a different and very important thing, which is extension of your dispersion now, is a kinetic properties. Kinetic, that is the electrical properties. This you already studied in the dispersed system. Don't get confused. This is extension of that only, same as that of that. So this is one which is having electrical property because of the surface ionization. You have got the every surface of your colloidal particle. You have got some charged species. Because of the charged species, you have got ionization of them and creating a charge. That charge may be negative or positive, depending upon what functional groups are present. Sometimes in the Jupiter ion, you have got both, and because of that reason, you are having a charged species neutral, or it means it is not having a charge. The charge is approaching to 0. But don't think that if you are having the charged species both are equal and appearing as a 0, but the pH, it will change its ionization. Because of the particular change in the pH, your shifting in the ionization of one of the functional groups will be varied depending upon the pH, whether it is acidic or alkaline. You are going to have a charged species. Again, it will behave as a surface charge. So, see where you are going to use this. That is actually a GPAT question. The second line, what you are seeing in this slide, is a GPAT question. Isoelectric point. This one you are going to have in the GPAT like question. The pH is termed as the isoelectric point of the protein, and the protein exists as a Jupiter ion, and it will have the least solubility at certain definite pH, specific for each individual protein. The protein number of the positive charges will be equal to the number of negative charges at that particular pH, that net charge will be 0. When the charge is 0, the molecule will not be present in the ionized state. When it is not having any ionization, it will be unionized state, which is having a least solubility. It means you will get the highest yield. In the highest yield, say for example, you may get the point, sir, why it is very important as the isoelectric point of the protein is important to us in our pharmacy. I think you may be having this one very much important, your Covishield. If you see Covishield, that is technology based on the, you will be having a mRNA based technology. That is nothing but your polymer containing the charges. That is actually mRNA based. mRNA you have got nucleic acids. They are containing amino groups also, carboxylic groups also. So you want to get that as a specific precipitate. Later onwards, you want to prepare any formulation. In that particular case, what you do? You want to get a good yield from your medium, because you are preparing mRNA by recombinant DNA technology. If you are doing that preparation, you want to get a greater yield. When you want to get a greater yield, what do? You need to apply the pH lot of yield. Then you can convert that particular into a delivery system after removing, and that is a purification, and you are converting it, because you have got so many precursors and your raw materials and media materials from the fluid. You need to get this specifically. This isoelectric point is specifically very important in those conditions. You need to estimate it where it is coming there, because we need to take discharge zeta potential. We have already seen in the zeta potential how you are going to use the technique. Electrophoresis techniques are present. We have already seen. So those techniques, it will be movement of these charged species and how fast they are moving. The potential will be known. So by doing them, you are finding out a change in the pH of how it is making it to potential to 0, and fix that in your broth and get your yield very high. This is very excellent concept to have a find out the isoelectric point for any protein, so that you will be having a highest yield. This is how it is based on the electrical double layer. This isoelectric point, whenever coming to that one, why it is having to the isoelectric point? Because you are charged at the surface, you are replacing. Where it is that surface? It is having at the exterior, not in the interior, not in the Sten layer or Nernst potential. We are talking about the charge at the zeta potential. This zeta potential charge is made to isoelectric point, not the Nernst. Do remember, Nernst potential is nothing to do with our case, because it is already hidden, and it is having a layer in the AA interface. But we are talking about the BB interface. In this diagram, if you have got 3 interfaces, one is AA. That AA dash is actually what the Nernst potential is. That is actually present on the surface, that is functional group of your molecule. This is existence because of the changes in the pH, and it is dominating there in the molecule itself. But on the surface of the diffusion layer, when it is moving, that not only moves, it will take associated, that is Gegen ions or counter ions are also moving with them. That is the reason the surface of the particular colloidal dispersion, because most of the colloidal dispersion proteins are colloidal dispersion. Whatever the vaccines, even now you may be having listening the news that Bharat Biotech is preparing nasal. In the nasal, when you are making it is a protein-based nasal vaccine, then you need to employ this double layer concept and find out the surface charge. When you are having a surface charge determination, then you are going to take that surface charge to electroneutral region. Then you are going to get a greater yields. After that, you are taking them and separating them and adjusting the isosonicity. You are adding adjuvants. I think you may be listening in the news that America is objecting not to give the adjuvant to enhance to supply, because we are depending on them. We need to prepare ourselves. So these adjuvants are added to enhance the vaccine efficacy. After that, we are making preservative. Then we are giving in the form of particular dose. This is actually what the journey is. You may be thinking that how they are making it, how they are making. This is the simple concept what you have learned now and applicable there. This is the reason you need to assimilate this. It is appearing as a complex when you read as a normal person in the newspaper, how these scientists are making this and how they are making the formulation and how they are launching it, what are the problems they are facing, and why the company's cost is very lesser than another company's cost, why this technology is varying. So these are all the buzzwords we need to have an answer, because we are all pharmacists. For pharmacists, we need to learn all these concepts without any skip, because it's based on this only we can proceed. Otherwise, even if you complete B.Pharm also, the questions like how they are preparing, how you are preparing like a layman. So this is the reason I am telling you these concepts which will be helping you forever. So in this AA region, even though it is present, existing, we are reading it, but we don't consider it in our isoelectric point. We are considering for our charge neutralization only the interface B, B dash, B naught. Whatever it is present, that is actually called as zeta potential. The B naught, BB layer plane is zeta potential. And beyond CC, what you are seeing here, it is a neutral region. So you are finding both the anions and cations are present. Even if you don't exist also, it will be neutral, because it is an equilibrium with charge. It will exist in it. So we don't bother about it. It is already present. We are bothering about wherever it is having a charge. In our isoelectric point, it is going to give us a problem. So we are going to exist that a surface charge. That point we are taking into the consideration here. Generally, when you are having a repulsion, when you are having a low yield, if it is the isoelectric point is deviated, then what will happen? Zeta potential is coming less than plus 30 millivolts, and it is more than 30 millivolts, minus 30 millivolts. What is this plus and minus 30? So the plus 30 is what you have got is repulsive forces, they are charge presences, and the minus 30 is attractive forces, they will be dominating. So both are they will be present either because of the charge of a positive cations or negative anions. They will be present. When these charges are approaching to zero, these charges are approaching towards zero, it means your colloidal is approaching to zero charge. Its repulsion is very less. When the repulsion is very less, attractive force exceeds. When the attractive force exceeds the repulsive force, you will get a aggregation of the colloidal particle. You will get a precipitate of that. That is the reason you are getting your proteins coming out. Your proteins we are coming out at the isoelectric point. You see how all are linked. Another one is when it is precipitated. If you want to exist as a separate one, then it is a destabilization. If you want to make a stability, you need to create a repulsion. If you want to create a repulsion, you need to create a charge. If you want to have a charge, you need to add electrolyte. If you are adding electrolyte, they are separate, then colloidal dispersion is stable. It means if you want to prepare a delivery system as a stable colloidal system, you are creating the charge more than this 30 millivolts, that is plus side or minus side. Then you are going to have a stable. If it is less than that, you are going to get an unstable colloid, because they will get a precipitate, and again they will be getting a sediment. That is the phenomena is against to our Brownian motion, and we don't have the advantage of your colloid dispersion when compared to your force dispersion. Same as that of force only, your dispersion is getting settled, because it is a poorly stable colloidal dispersion. This part we are going to study in the stability of dispersion in the next classes we are going to have. In the next class we are going to have, this is very important concept, because based on this zeta potential only, we are going to have roaming around this to find the stability of the colloidal particles, and that value we are going to take. So the zeta potential decreases more rapidly when the concentration of electrolyte is increased, or valency of the counterions are increased. This one we have already seen in the previous case also. Now we are coming back to our DLVO theory, how this theory is impacting our double layer. And according to these four scientists' theories, the theory is named as Vt is equal to Vr by Va, where the Vt is the result, that is the interaction, that is the potential energy interaction between the particles, that is the total or net, that is Vt. It is a result of repulsion due to the electrical double layer, that is Vr, plus attraction due to the van der Waals forces, that is Va. both are together, you are going to have a net charge. That is actually a VT. VR depends on the several parameters like a zeta potential of the system and the particle radius and interparticular distance and electrical dielectric constant of the medium. These parameters are GPAT questions. You are going to get what are the parameters. Whereas the factors that affect VA, that is van der Waals attraction, is diameter of the radius, interparticular distances. So even though the charge is more, interparticular distance is more, it is going to get less and lesser. Then what will happen? You are going to have an attraction. When the particle radius is bigger and bigger, then what will happen? The molecule will become and bigger. It will tend to form a sediment. When it is forming as a sediment, the particles are coming closer. When they are coming closer, according to DLVO theory, they will get attraction. That's what it is seen in this particular diagram. If you see here, it is containing two attraction